Static analysis is the process of evaluating code for errors, memory leaks, and security vulnerabilities. The static part of static analysis refers to the fact that the code is not running when you're performing this analysis. This differentiates it from unit tests and integration tests, which typically evaluate the runtime characteristics of code. If you use an IDE or a linter, you are using a basic form of static analysis all the time. More sophisticated static analysis tools can be used to analyze code in sensitive domains like healthcare or automobiles. During static analysis, we can discover problems in the code by evaluating the structure of a program. Buffer overruns can be identified before they turn into a vulnerability like Heartbleed. Null pointer exceptions can be fixed before they cause a segmentation fault in production. Concurrency issues can be serialized before they result in a problematic race condition. Today's guest, Paul Anderson, is the VP of Engineering at Gramm, where he works on Code Sonar, a static analysis tool. We discussed how static analysis works, why it's useful, and how it fits into a modern software delivery pipeline. Full disclosure, Gramm is a sponsor of Software Engineering Daily. To build the kinds of things developers want to build today, they need better tools, super tools, like a database that'll grow as your business grows and is easy to manage. That's why Amazon Web Services built Amazon Aurora, a relational database engine that's compatible with MySQL or PostgreSQL, and provides up to 5 times the performance of standard MySQL on the same hardware. Amazon Aurora from AWS can scale up to millions of transactions per minute, automatically grow your storage up to 64 terabytes if need be, and replicate 6 copies of your data to 3 different availability zones. Amazon Aurora tolerates failures and even automatically fixes them and continually backs up your data to Amazon S3. And Amazon RDS fully manages it all, so you don't have to. If you're already using Amazon RDS for MySQL, you can migrate to Amazon Aurora with just a few clicks. So what you're getting here is up to 5 times better performance than MySQL with the security, availability, and reliability of a commercial database, all at 1/10 of the cost. No upfront charges, no commitments, and you only pay for what you use. Check out aurora.aws and start imagining what you can build with Amazon Aurora from AWS. That's aurora.aws, aurora.aws. Paul Anderson is the VP of Engineering at Gramm. Paul, welcome to Software Engineering Daily.
Thank you, Jeff. Glad to be here.
Yes, it's great to have you. And today we're going to talk about static analysis and some of the related technologies that are in the field. This is a field that's been around for a while, but it continues to be important and it evolves quite rapidly. But let's just start off with a basic introduction to some of the concepts in static analysis for people who are totally unfamiliar with the field. Explain what static analysis is.
Sure. So static analysis is basically any process that computes a property of your program without actually executing the program. So it's often described in contrast to dynamic analysis, where you're executing the program. And everybody's familiar with dynamic analysis because that's what you do when you do testing or when you run a memory checker or something like that. Static analysis is designed to compute these properties by simply reading the text of the code, and there are various algorithms to compute those properties depending on the kind of property it is. And the properties can range from things that are very surface level, very syntactic or even lexical, to very deep properties of the semantics of the program. Now, historically, static analysis tools started out as tools that found problems with your type system in your program or other kind of superficial surface level things. And so many C programmers are familiar with the lint family of tools that basically started very shortly after the C language was first defined. Since then, they've gone through a period of resurgence, so they're now used for many different kinds of things. They're still used, of course, to find superficial properties like the lint family would, but also things like conformance with coding standards and extraction of code metrics and things like that. But the most recent class of static analysis tools, which I refer to as advanced static analysis tools, are those that are whose primary purpose is to find bugs in the program. And there are a few properties of those kinds of tools that are important if they're going to be effective at finding bugs. One is that they need to be whole program. That is, they look at the entire program as a whole, so they can compute how information flows from one part of the program to another across compilation unit boundaries and across procedure boundaries. The second aspect of them that's important is that they are path sensitive. So what that means is that they are computing properties that hold along particular executions through the code. And in order to do that, of course, you require fairly sophisticated algorithms under the hood.
So the basic static analysis tools that people might be familiar with are linters or even an IDE. If I've got Eclipse or Visual Studio Code, it can identify that I'm missing a package or I have not initialized a variable that I'm trying to use. And because of the properties of the language, the IDE, interactive development environment, can infer that there is a problem with my code. Those are the simple explanations, the simple examples of static analysis. Also, linters would be another example. And
Yep.
you're referring to also some more complex and subtle techniques that can identify more subtle problems. And I want to get into some of those subtle problems, but let's stay at a high level for a while. What is a developer trying to accomplish when they are running static analysis over their program?
So the main reason you run static analysis is to find problems. And the problems can range from I didn't conform to my coding standard. Maybe you've got variables that have to be named a particular way and you didn't do that. And so you can use a static analysis tool to find that kind of thing. They can also be used to do metrics computations. So if you've got a standard where your cyclomatic complexity, say, must not exceed 15, then you can use them for that. They're most useful, we believe, though, for finding real bugs. And so they're typically the finding bugs that are unlikely to be found using other techniques. So the key thing about static analysis is that the results that it can compute are in principle good for all possible executions of your program. So when you run a test, you're running it against a particular set of inputs. So the results you get are only good for those set of inputs. And obviously you try to have a very comprehensive test suite that exercises lots of the program. But that's infeasible for all but the most simple programs. So what static analysis tools are really, really good at are finding the cases, so typically execution paths or particular values of variables that trigger unusual bugs. So if there's a corner case and the person who wrote the test cases wasn't particularly good about thinking about corner cases, then the static analysis tools are really, really good at finding those kinds of things.
Mm-hmm. Are there some limitations on the types of language or the format of my code that it needs to be in order to do static analysis? For example, do I need to have a typed language? Is it because, for example, we did a show recently about TypeScript, which is a typed, or you can use types with it. It's a layer on top of JavaScript. Essentially, you compile TypeScript down to JavaScript, and it adds typing, which makes it easier to work within an IDE, for example, because it gives you some assurance around what types of variables are you passing from one place to another. So are there limitations on the language style or the framework that you need to be working in order to perform static analysis on your code?
Well, in general, no. So you can run static analysis in basically any program you like. But of course, the static analysis tool has to be able to understand that language, and it has to have, if it's looking for deep semantic properties, then it has to have an understanding of the semantics of that language at a fairly sophisticated level. It is certainly easier to do static analysis on a language that's typed, because types constrain what programs can be constructed in that language. And if that information is available, then you can get better results out of a static analysis tool. But you can basically run, in principle, static analysis on anything, any program.
Including binary analysis, which is something that I didn't really know until I started researching for this episode. Binary analysis can be used to analyze programs that are already compiled. They're in binary format. Why is that useful?
So there are two major use cases for binary analysis. So the first is somebody hands you a program, an executable, let's say, and they expect you to run that program on your computer. And if you're sensitive about whether it's safe to run that program, then you might want to run a binary static analysis on that to determine if it contains things that might be just plain old bugs, or things that might cause the program to be exploitable by an attacker. And that's particularly important for organizations that are running very highly secure environments where they're taking code from suppliers, and they don't necessarily trust the supplier to give them code that's safe. The other use case is where you're using a library and you don't have source code for that library. Now, this is pretty common, actually. In fact, it's almost universal for at least for compiled languages. So if you're running a C program, you compile the source to binary, but you're linking it against things like the C library or against your operating system libraries that might handle things like graphics or communications or something like that. And you rarely have all the source code for everything that's in there. So what you can do is take your source code, do the static analysis on that, and then augment that with the analysis of the library that you're linking against. And what this means is that you can get better results. See, if a source static analysis tool can't understand what the semantics are of the library that the source code is calling into, then it basically has to give up. It can't compute any interesting information about having called those functions. And typically, static analysis tools, they don't stop; they continue going, but they can't really say anything intelligent, and that results in both false positives and false negatives. So by having an analysis that takes into account those binary libraries, you can get better results.
What do I need to know about a binary in order to analyze it? I mean, I think about a binary as just this blob of ones and zeros. Do I need to know something about the architecture that it was compiled for, or the operating system it's going to run on? What do I need to know?
Yeah, so there are several things. So first of all, let me just clarify here that when I talk about binary analysis here, I'm talking about the binary analysis that CodeSonar does. CodeSonar is our static analysis product. It's primarily for source, but it also works for binary. There are other static analysis tools that work on binaries, but they may work in a different way. So when I talk about this, it's really about what CodeSonar does.
That's a fair caveat.
Yeah. So what CodeSonar does is designed to be able to analyze x86 or x64 code or ARM code. So if you have your library in one of those formats, then CodeSonar has a shot at being able to analyze it. Now, of course, yes, you're right. It's just a file containing lots of ones and zeros. So the binary has to be in a particular form. So there are lots of standard forms. There's ELF and dwarf and things like that that are standard formats for binary files, and they contain meta information that's useful to understand where to look in the file to find the actual code. And then the other thing that's important is once the code has been disassembled and transformed into a representation that the analysis can then work on, What's important is what we call the ABI. That's the application binary interface. So that's the rules that define what happens when a function in one part of the program calls a function in another part. So it tells the analysis needs to know about how the parameters are passed to that function and how the return values are then communicated back to the caller. So it's important to know that so you can identify function calls, because if you can't identify function calls properly, then you don't have a good way of doing a whole program analysis. So having it in a standard form, having it be one of the processors that we recognize, those are the most important things.
I sell podcast ads, and podcast ads are a weird commodity. Many of my potential customers are not actively looking for podcast ads, so I have to reach out to them with a cold email. This cold email process is what lots of people go through, whether they're marketing a software product, a newsletter, or an online course. I know there are a lot of people who are listening to this who are building some kind of new software product, and they're trying to figure out how to sell it. If you're building your own business, you have to learn to sell, and if you're going to sell, you have to learn to prospect. Prospecting is the process of gathering email addresses and sending messages to potential customers. Prospect.io is my favorite tool for prospecting. You can find email addresses of people at any company. You can find email addresses of users on LinkedIn. After you find those emails, you can use Prospect.io to manage your prospects and to send emails. You can see when somebody opens your prospecting email, and you can stop sending those emails when they have signaled that they're not interested. If you're building a product, you have to find customers to sell to. How do you find customers? By prospecting. I've tried a ton of prospecting tools. Prospect.io is my favorite. Prospect.io is offering Software Engineering Daily listeners 20% off your first 2 months. Just mention SE Daily to Prospect.io support after you sign up. And if you're selling something, try out Prospect.io. I hope you enjoy it. Let's say I take a piece of third-party software and I run binary analysis on it because I just get this software off the shelf. Let's say I run a company that makes helicopters, and I've got this third-party piece of helicopter software. I need to be pretty sure that this software works, because otherwise my helicopter might crash. So if I run this binary analysis on it, I find some kind of vulnerability or a problem in my helicopter software, do I have any recourse? What am I going to do? Because I don't actually have the code that the binary that compiles to that binary. So what can I do if I identify a problem?
So there are several things you can do. So the most sensible thing to do, and the thing that the helicopter supplier would probably do first, is to reach out to the supplier and say, hey, there's a bug in your code, fix it please, and send me a new version. Now, that's not always possible. So we've run into organizations that are using legacy code, and the original supplier is long out of business, and the original team is gone, and maybe the source code isn't even around anymore. So in that case, there are a couple of things you can do. The easiest thing to do is to avoid the bug. So typically when we give a report, it's along the lines of, let's say it's a bad memory reference. So we'll say you got a bad memory reference at this instruction, but in order for that to be triggered, for it to actually cause the program to crash, then these conditions must hold. And you may have control over those conditions. So it may be it's in a function, and if you call it where the second parameter is null, then you'll get the crash. And maybe you have control over how that function is called in your source code. So you would put in a guard in your part of the code that says, make sure that you never call this function with the second parameter being null, in which case you avoid it. And that may work, it may not. Sometimes you can't really avoid it. In that case, what you have to do is basically patch the binary. And that's tricky, but it's certainly doable. I've heard stories of organizations running binaries in safety critical code where there are dozens and dozens of binary patches that allow the system to operate correctly, even though the underlying code was originally broken.
Can you give another example of a bug that somebody might find in the binary analysis process and what they would do in response to that?
Right. So with Code Sonar, roughly speaking, you can think of the kinds of problems it finds as falling into three categories. So the most important ones are places where the code is it's triggering some kind of undefined behavior. So a bad memory reference is a good example, like a buffer overrun or a null pointer dereference or a data erase or something like that. Those are the most important things. The second category is where the program is using an API, but it's breaking the rules. So if you close the file descriptor twice, or if you use memory after you freed it, those are in that category. And the third category are things that are kind of superficial. They don't or are unlikely to cause your program to crash, but they're suspicious looking. So a cast that's invalid is a good example, or redundant code is another good example. So with binary analysis, in principle, you can find instances of problems in the first two of those categories. Binary analysis is not great for that third category, the superficial problems or the suspicious looking code. But for finding places where there's undefined behavior or where an API is being used in an incorrect way, then roughly speaking, it'll find the same kinds of things that it would find in the source if the source were available. Now, what I said before was that roughly speaking, you can find the same kinds of problems, and we've seen this in real life. We take some source code that has a bug in it, and we compile it to the binary, and we can find the exact same bug in the binary. But in fact, there's a very interesting class of bugs that don't show up in the source at all. So they can happen because of various reasons. So one is the compiler might have a bug in it. So the compiler could be generating incorrect code. And that's certainly happened plenty of times. The other reason, which is actually a bit more interesting, is that the compiler has made an assumption that is at odds with the programmer's assumption. And there's a really, really good example of this a few years ago in the Linux kernel. So in C, the rule is that if there's undefined behavior in your program, the program can do anything at all.
Right.
So this is referred to sometimes as the catch fire semantics, meaning that according to the rules of the language, your program is allowed to catch fire. So the only thing that a compiler writer can do that makes any kind of sense is assume that your program does not have undefined behavior. And the compiler writers, they exploit that fact in order to do optimizations. And some of those optimizations are kind of surprising. In this Linux kernel bug, the code was dereferencing a pointer. This was in the kernel. The pointer was null, or it was close to null. It was in the range of addresses that are close to null, that are invalid to access. Now, in this particular platform, it was actually okay to do that because it was some kind of embedded system in which it was okay to access the 0th page of virtual memory. But the compiler didn't know that. So the compiler saw the dereference and concluded that it couldn't happen. And as a consequence of that, it optimized out some code that it concluded was unreachable. And that code turned out to be kind of essential to maintaining a security property. And as a consequence of that, it opened up a security vulnerability in the kernel.
Wow. This is interesting because you're kind of describing I always had an impression of compilers as being fairly objective. Like they just translate your higher level code into something that is lower level and is a one-to-one mapping. But you're describing a subjective decision that the compiler made to essentially obviate this code path because it looked like it was invalid or unsafe for some reason, but it was actually a feature and not a bug.
Yeah, you can think of it that way for sure. And there are lots and lots of examples like this. So I'm particularly fond of examples that are that show up in concurrent programs because they are extremely subtle and very, very difficult to find otherwise.
And this is
So
what you studied in your PhD, right?
yeah, that was a different aspect of concurrency, but yes, my PhD did have to do with parallel programming and computer architecture. So let me, if I may, describe some of those examples because they
Please.
are sometimes very surprising to people who hear about them. So a data race is, according to the language specification, undefined behavior. And like I said earlier, anything goes if you have undefined behavior. So the only thing a compiler writer can do is to assume that it can't happen. So a data race is when you've got one or more threads of execution in your program. You've got shared memory. Those threads are accessing some location in memory, and at least one of the threads must be writing. So as a consequence of that, the third condition, is that the writes and the reads are not protected by a lock. So with multi-threading, this is commonplace. Anybody who's written multi-threaded code knows what I'm talking about. So now unusual things happen because if you don't have the locks, then because the compiler can do optimizations in the presence of data races, then very strange things can happen. So one of the things that compiler optimizers do is code motion. So programmers think of when they write a sequence of statements, A, B, C, D, that they will be executed in that order. But if there aren't any hard dependencies between those statements, then the compiler can put them in a different order. And they do this all the time. This is what optimizers do. And they do that because maybe a different order gets them better locality in the cache or something like that. And if you're optimizing for speed, then that's a good thing, right? But if the compiler is compiling something that is a race condition and the programmer assumed that the code must execute in a particular order, then the data race condition that looks entirely harmless can be converted into something that's basically broken.
Mm.
And there are some very sweet examples of that I can go into if you like, or I can give you a reference to it later.
Yeah, let's talk about it a little bit later, perhaps. I wanted to get into more of a discussion of the usage of static analysis. We've given a broad overview for how and why it's useful, but I'd like to talk about the process of using it. Like, so at what phase in the development process should I run my static analysis tool? Like, do I do it while I'm building my program, or do I do it during the deployment process? When is it useful to actually run a static analysis across my program?
So the earliest you can run the static analysis, the better, because the earlier you can find a bug, the cheaper it is to fix, and the cheaper it is to find, of course. So as soon as your program is compilable, that's when you can start to get some value from the static analysis. Now, you can run a static analysis, at least for CodeSunner, maybe other tools are slightly different. The smallest unit in which you can run the analysis is a translation unit, a compilation unit. So if you've got a C file or a C++ file and you can compile it, that means you can run it through the static analysis and you can start to get value. Now, of course, the results that you get from a whole program static analysis tool are better if you have as much code as possible. You can then take that C file that you've just written and analyze it alongside the rest of your code, and you can get better results. But the issue is that the more code you analyze, the slower the static analysis is going to be. And you could end up in a situation where you're not willing to pay the cost of doing an analysis, a full analysis of the entire program in a very tight edit, compile, debug cycle. So what people do is they basically run a lightweight analysis, maybe of just a compilation unit at a time or some small module at a time, and during development. And then when they commit or before they commit, they do a larger scale analysis. And then often what we find is that organizations, as part of their continuous integration setup, they will run a static analysis of the code as soon as it's committed to the repository. It's not the only model, of course. Some organizations, they will do a nightly static analysis of everything. And that way people come in the morning and they have in their inbox static analysis reports that they can then act on. And they can see easily from that the set of warnings that have been introduced since the last time it was run, and that typically corresponds with the changes that they made the previous day. So with some combination of those things.
If I run my code through static analysis, is it always clear-cut when there is an error or a vulnerability that I should be dealing with, or is there some gray area with identified problematic patches of code?
It depends on the property that you're looking for. So very superficial properties, typically the static analysis is very precise about those. It knows exactly when the property has been violated and exactly when it's not been violated. So something like, let's say you forbid goto statements. Well, it's really obvious for the most part that you have goto statements. So there typically aren't any gray areas there, assuming that your programmer hasn't gone out of his way to try to conceal such things in a clever manner. But for the really interesting properties, there are both false positives and false negatives. And this is true of basically all static analysis tools that work on general purpose programs. So in static analysis, you basically have a trade-off between three things. There are more factors than this, but let's simplify it by talking with just three. And the three things are precision, that is, how good are the results? Are the results all true positives, or are there lots of false positives in there? So a very high false positive rate means you have very low precision. And perfect precision means that you've got no false positives whatsoever. The other factor is recall, and recall is the ability of the tool to find real bugs. So a tool that is perfect recall is finding all the bugs that exist in the program. And then the third corner of the triangle is performance. So a tool that is really, really good at precision and really, really good at recall is likely to take quite a long time to run. You can find really superficial properties with an analysis that runs quickly. But the really interesting bugs that you want to find, you need to pay some cost in terms of performance. And these three things, the precision, the recall, and the performance, they're at odds with each other. So it's like when you're buying a car, you can choose fast, cheap, or good. With static analysis, you can choose any two of fast, cheap, or good. With static analysis, you can choose, roughly speaking, good precision, good recall, or fast performance. And each of the tools finds their own kind of sweet spot in that trade-off space. And each of the tools allows you to some extent control where you are in that space. So somebody who's developing a safety critical device for an aircraft, for example, they're going to want very, very high recall, meaning they want to find as many bugs as possible. They won't be too bothered by false positives, because if there are lives at stake, then it's worthwhile taking the time to go through all those. And they're going to want to pay the price in terms of performance. Whereas somebody who's writing, let's say, a game for a cell phone or something, then they're probably not all that interested in pouring through lots of false positives in order to get at the real bugs. They're more likely to care about the most common bugs, and they're also driven by new features, so they want to get on to developing the new feature as quickly as possible.
Spring Framework gives developers an environment for building cloud-native projects. On December 4th through 7th, Spring One Platform is coming to San Francisco. Spring One Platform is a conference where developers congregate to explore the latest technologies in the Spring ecosystem and beyond. Speakers at Spring One Platform include Eric Brewer, who created the CAP theorem, Vaughn Vernon, who writes extensively about domain-driven design, and many thought leaders in the Spring ecosystem. Spring One Platform is the premier conference for those who build, deploy, and run cloud-native software. Software Engineering Daily listeners can sign up with the discount code SEDaily100 and receive $100 off of a Spring One Platform conference pass, while also supporting Software Engineering Daily. I will also be at Spring One reporting on developments in the cloud-native ecosystem. I would love to see you there and have a discussion with you. Join me December 4th through 7th at the Spring One Platform Conference and use discount code SEDaily100 for $100 off of your conference pass. That's SEDaily100, all one word, for the promo code. Thanks to Pivotal for organizing Spring One Platform and for sponsoring Software Engineering Daily. We should be clear, this is code that is run. The static analysis is run offline. So when you're talking about speed, you're talking about the speed of an operation that is occurring in the development process. So although I don't want to understate that can be extremely cumbersome if you're running a static analysis tool that takes 80 minutes every time you're recompiling your program, that can be onerous if it's blocking you from continuing to make productive progress.
Yeah, that's right. So what people want is for the static analysis tool to take about the same time as the compiler takes. Maybe, a couple of factors, maybe 3 or 4 times, but that's what they want, and that's what we try to give them. Now, because you have control over where in this three-way trade-off space you sit, you can have a configuration that takes much, much longer and gets very much better results. And so you can do that. So in that case, if it takes 80 minutes or several hours, you can do that analysis overnight, where nobody's kind of sitting twiddling their thumbs waiting for the results, and look at the results in the morning.
Let's talk about some specific domains and how they might use static analysis. So we could talk about healthcare or the energy grid or autonomous cars. If something goes wrong in one of these domains, lives could be lost. And these are the tools where I think it's most important to have a extensive static analysis tool. How does static analysis get used in these domains? Maybe you could talk about whichever one is most interesting to you.
Right. So the sweet spot, we believe, for static analysis tools is dependent on the language. So with some languages, bugs that occur don't have much consequence. So if you're in a data center and you're running some kind of IT application and there's a bug in there that causes the program to crash maybe once in a blue moon, then the system will catch that exception and report it, and you'll get to it after some time, and somebody will try to reproduce it and fix it. So the consequences of that are not very dire. So static analysis for languages like Java or C# or Python or something like that for certain kinds of bugs isn't really as valuable as static analysis for a language like C or C++ or binary, where the consequences of an innocent mistake can be terrible. So in the same bug in a C program can introduce a security vulnerability. It can cause data corruption completely silently. It may not raise an exception. If you've got an out of bounds memory read, the program may just keep on going. So the sweet spot for us is programs that are written in those hazardous languages, and particularly those that are written for safety critical domains. So most of our customers are like that. They are doing medical devices or automotive or avionics or industrial control.
And one of the other areas that I hear being discussed in this type of domain is formal verification. Like, I have done some interviews about distributed systems where they talk about formal verification, proving that your algorithm works. I guess I'm not super familiar with that field, but how does static analysis compare to formal verification?
Right. So formal verification is primarily a tool that can give you very solid evidence that your program has certain properties. And if the properties that you want to prove are things like it doesn't crash or it doesn't have memory errors, then it is possible to have formal verification that will prove those properties of your code. Now, the disadvantage with formal verification is that in order to trust those results, you have to basically know everything about the program. And you have to trust that not only that the analysis that's doing this verification is doing the right thing, but that the people who wrote the analysis have made the right assumptions about things that cannot be known. So if you just take an off-the-shelf open source program like Apache or the Linux kernel or something like that, it's very difficult for formal verification to prove properties of those programs because they use features that the verifications have difficulty with, like threading, for example, or recursion or things like that. And furthermore, those programs rely on things like operating system libraries. And if you're to believe the results that come out of the formal verification tool, then you must also believe that it's making the right assumptions about interfacing with those things. And that's a pretty tall order for a lot of programs. Now, there are plenty of programs for which you can prove properties, but they tend to be fairly small in scope and in size. And they tend to outlaw certain key language features that are the kinds of things that you might want to rely on. So, for example, I've seen formal verification used very effectively in domains where, let's say, crypto, for example. So with crypto, you've got some input data and you've got some output data, and there's a transformation on that, and you want to prove certain properties of that. Then that tends not to have too many dependencies on things that are unknown. It's not going to call into the outside libraries very much. So it's plausible that you can do very good formal verification of things like that. Now, the other thing that a proof must rest on is, again, I'll come back to the undefined behavior in the language. Like I said earlier, if there's any undefined behavior, then the compiler can do anything and the program can do anything. So in order to prove the property that you're interested in, then you must also prove that there's no undefined behavior in your program, which is a step that's often kind of swept under the carpet, because to do that is probably just as difficult or more difficult than proving the property that you're interested in the first place.
I feel like we've been talking at the medium to high level about how static analysis works, and I'd like to go a little bit deeper into the weeds. So you talked about concurrency issues as one of the methods, one of the problems that static analysis could detect. Let's talk a little bit more about the concurrency issues. There's some other low-level things I want to get into, but explain how static analysis can be used to avoid concurrency issues. What's a prototypical example of where that would be useful?
So there are some examples that have to do with how you manage your locks. In a multi-threading system, if you've got any kind of shared resource, then you better be using locks or maybe a lock-free data structure to access that shared resource. And there are certain rules for using those locks that are not unlike the rules for using other APIs. So you shouldn't lock the same thing twice, or you shouldn't attempt to take a lock on something when you know for sure that it's already locked. So the same kind of technology that we have for finding problems with non-concurrent APIs can be used for finding problems with APIs that have to do with multi-threading. But the real value, I think, is finding things like the data races, as I mentioned earlier. You can find certain kinds of deadlocks relatively easily by looking at patterns in which locks are acquired and released, and other similar things. But the real value is in things like finding data races. So the way the static analysis works for finding data races is, so it finds all thread entry points and assumes that the threads can be running concurrently. and it then looks at the memory locations. These are typically variables or access paths through variables that are accessed by those threads, and it computes the set of locks that are held when those accesses are made. And then it's a big constraint system. Essentially, you know that there are possible executions, you know that there are accesses to variables, and you know which locks are held. And so it looks for inconsistencies in those. So if it sees that the set of locks when you write to a variable is different than the set of locks when you read from the variable, then that's immediately suspicious. And then there's a further phase that will then kind of refine that into a warning report that you can then look at and understand.
Another lower level topic we could discuss within static analysis would be buffer overruns and null pointer exceptions. Describe how an error like these things would be detected in a static analysis tool.
So it's a similar kind of thing. So one way of thinking of the kind of static analysis that CodeCenter does is that it explores paths through the program. So when it creates the representation that it's then going to do the analysis on, that representation, one of the primary parts of it is what we call the control flow graph. And so that's just a model of each function that allows the analysis to reason about the paths. So each node in this graph corresponds to a statement, roughly speaking. And you have decision points in which control can flow to some subsequent point. So if there's an if statement, there's a decision point there, and so that will cause a branch in the pathing. So when the analysis sees a decision point, it first explores what could happen down one path, and then explores what can happen down the other path, and when they join up again, it can choose to follow the conclusions it made on each path subsequent to that point. So when it's doing that, so that's a little bit what you would do if you were sitting down with a piece of paper and looking at some code and trying to reason about how it executes. It's creating a set of equations that model the abstract state of the program. So one way to think about this is that those equations represent things like the value of this variable x is 0, or y is less than 2 times n plus 1, or the length of this buffer is z, or this file descriptor is in state open, or things like that. So there's a whole domain of properties that are represented in terms of these equations. And so a buffer overrun is going to take place at a dereference of a pointer with possibly an offset. So these equations will model what the possible values of that pointer are and what the values of the offset are. And if it sees that the values can be out of range, then it will look at that more carefully and determine if, in fact, it's feasible to execute that particular path with those particular conditions. And if so, it'll then issue a warning. And the warning will then end up going into a database, and then, at least with CodeCenter, that's how it works. And then there are interfaces to that database, typically through the web client, that allow you to see the results.
Earlier, we talked a little bit about the idea of third-party software that you would need to run static analysis on to verify that it's legit. I've heard of supply chain issues where you get there's some foreign entity that's making your servers, and if you're buying servers from one of these foreign entities, there's a risk that it's got some software on it that you don't want, like some stuff that's been tampered with, whether we're talking about webcams or server software. Can you use static analysis to ensure that the lower level software that's used on those pieces of hardware has not been tampered with?
So yes, you can in principle. So it depends, of course, on who's doing the tampering. So if the manufacturer is an organization that you trust to do the right thing, and you're worried about somebody in the middle who's tampering with the software, then the solution there is probably not static analysis, at least not on its own. The solution there is more like secure boot or computing signatures of the images, the binary images that you're going to be executing, and confirming that they are the same as the signatures of the stuff that you will be executing in the field. If you're worried about the manufacturer itself, putting vulnerabilities into the code that you're going to be running, we'll refer to that as insider attack, because it's somebody who has permission to edit the code and they're deliberately putting problems into it so that some malicious party can exploit them later. That's happened. It's certainly not uncommon, and you can use static analysis to do that. If it's a situation where the attacker is putting in a vulnerability, then they will try their hardest to make it look like it's innocent, because they don't want to be caught and blamed for this. And so an inspection or testing of the code may not reveal that, but static analysis can, at least in certain circumstances. And in fact, there's a really interesting story that came out a few years ago of just this kind of tampering. So there's an internet relay chat server called Unreal that's used very, very widely, and it's open source. And so hundreds, thousands, tens of thousands of individuals have downloaded it and used it. And of course, that's a server that's sitting in the internet, so you want it to be secure, right? What was found was that some insider, somebody who had access to the source code somehow, and I don't know exactly how they did this, maybe they corrupted the repository or something like that. But in any case, what they did was they put in some code that was designed to put in to have a back door into that daemon, that server. And it was triggerable if somebody came along they connected to an instance of this and they typed in a certain string, it would look at the contents of that string. And I think if the first characters were capital A, capital B, semicolon, then it would then basically the remainder of the line would be executed as a command on that server with the same privileges as the server. Now, the interesting thing about it is that the code was deliberately disguised to look innocent. So there was a macro that was called, I think, debug3 dolog or something, which made it look like it was only something for doing debugging during development. And then there was another macro that disguised what was going on under the hood. And these macros were defined in different places in the code, so it wasn't immediately obvious by just inspecting the code what was going on. But the static analysis saw right through that, because in order to do its job, it had to run the preprocessor, it had to create an accurate, precise program model, and it immediately saw that, hey, here's a call to system, and it looks like system is getting its data from an insecure channel. CodeCenter does this, what we call taint analysis or hazardous data flow analysis. So it was able to flag immediately that there was a problem, having seen through all the disguises that the malicious attacker had inserted in order to fool the reader.
Well, I want to begin to wrap up and just discuss a little bit about Gramm attack and what's going on with the company right now. You've been working on static analysis and related tools for 26 years, which is a long time for a software company. And today you do research projects with the government. You have products like Code Sonar that are accessible to plenty of developers. So I'd love to just get an overview for how the company has evolved to where it is today, what kinds of things you're working on, and where you're going in the future.
So we're a spin-off of Cornell University. The co-founders were a professor there and his then graduate student. And the grad student had won the ACM Doctoral Dissertation Award for his PhD thesis. And that described a system called the synthesizer generator, which you can think of as a precursor of the modern IDE. So it was a system that would generate language-sensitive editors for you. You would give it a grammar, and it would compile that grammar into a system that allowed you to construct programs that were consistent with that grammar. And it was used a lot for research projects. We had a product that that essentially did static analysis and interactive editing for Ada programs for many years, and that's how we got our start. So that evolved into static analysis in a more sort of general sense, not just for those programming languages and using different technology. And because we have very strong roots in the academic community, we started to do research that's very much like academic research as well. And that's always been oriented towards doing static analysis, dynamic analysis of programs in order to find either bugs or maintainability problems, or to do automatic protection or automatic defenses and things like that. We had a pretty nice victory last year where the government ran the Cyber Grand Challenge. So that was a capture the flag competition where the programs, so the competitors in this competition were completely automated, and they were all put in a virtual arena, and they had to battle it out amongst each other to try to break into each other and to defend against being captured by the opponents. That was a competition that started out with 120 or something organizations. In the final, there were, I think, 7, and we came second in that. So that was, we're proud of that, and we're working on transitioning some of the technology that was used during that competition to other things.
Well, it's been great talking to you about static analysis and the ways that Grammatech has evolved. You know, I look forward to seeing how the company evolves going into the future, and I want to congratulate you on all the work that you've done.
Well, thank you.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/sedaily. That's symphono.com/sedaily. Thanks to Symphono for being a sponsor of Software Engineering Daily for almost a year now. Your continued support allows us to deliver content to the listeners on a regular basis.
Wow!